Greetings. In this presentation, we're going to look at three key insights from modern neuroscience and how they apply to how we teach about reading, math, as well as maps, and in fact, why we should be doing map lessons already in primary school. So let's start with three observations from actual classrooms. Observation number one, when my students tried to remember a map. I was showing a class some pictures about environments in Africa. This is what a rainforest looks like from the air. The location of the rainforest on Africa is here, right near the equator. There's lots of rain, great big trees. Of course, it's a rainforest. And you make your house out of wood because there's lots of wood around. It's easy to make a house out. You put it up on stilts because it's hot and rainy. And this is what a desert looks like. It's located here, up near the tropic line. It has very little rain, no trees, because trees need water. If you don't have any trees, you don't have any wood, you're going to have to make your house out of something else. So houses are made out of dirt or stone. Like I say, it was just a simple video discussion of different environments in Africa. And then I gave them the assignment. Study the pattern of the environments here. It's a really important background for a lot of topics. This is a regional map of natural environments in Africa. And then about 2 weeks later, there's a quick pop quiz. Divide this blank map into 3 to 6 natural regions and write a short phrase to describe each region. Here are some of the actual answers. And what I did to make this real easy to compare is I just scanned their map and recolored them with the colors of the original study map. Now, this is what the original study map looks like. And you've still got it in your short-term memory, but it's obviously gone from the memories of these students. I mean, every single one of these students turned the dry Sahara into cropland. 3 of them put the rainforest way south of the equator. 1 of them pushed it off of Africa entirely. It just disappeared completely from their mental map of Africa. The fact that you would come out of this, and it's reinforced by an awful lot of research, is that human brains do not store map images accurately. And if this is your mental map of Africa, you can't possibly understand where malaria is, or the spread of Islam, colonization, slavery, climate change, terrorism today. Repeat, human brains do not store map images accurately. Popular opinion to the contrary, there really is no such thing as a visual learner. After reviewing the empirical research, a panel of psychologists concluded the contrast between the enormous popularity of the learning styles approach in education and the lack of any evidence for its value is, in our opinion, striking and disturbing. There is a handout at the website we'll show you at the end for anyone who still wonders about this zombie idea called learning styles. Developmental psychologists uniformly call it a neuromyth. It's just not true. Observation number 2. Students trying to put a symbol for their reading rub into a model of their classroom. These frames are from an explanatory presentation on the website that we'll look at later. To introduce the idea of representation in primary school, start with a model of a very familiar object. Ask them, what is this? I've done this in a dozen kindergarten and first grade classrooms. They say, oh yeah, this is a school bus. I say, wait a second, you're kidding. I can't fit in it. I mean, the door doesn't even open. What is this? And you try to get the students to come up. This is a model of a school bus. It's like we put a big bus in a shrinking machine. And then the really key insight, it represents a school bus, just like O represents the sound of O, and 4 represents 4 squares. This concept of representation can be taught with a geography lesson in first grade. Imagine that we put our whole room into a shrinking machine and made it the size of this box. And add the windows to the box before you lay it on the table there, and then have the students rotate the box so that it fits the room, so that the windows in the box are on the same side that the windows in the room. They need to own that idea of representation. And then a little bit later on, you say, what's this? This is the rug we sit on when we do our reading lessons. No, it's a model of our reading rug. It's like we put the big rug into a shrinking machine and made it small enough to fit inside the box. It represents our reading rug. And the instruction to the students, put this representation of the reading room where it ought to go in the model of our room. In all 5 classrooms in this school in New York where we did this, the students first put the rug in the middle of the room, and then they were high-fiving each other about how they'd done a great job. And then the teacher asks a really important question. Is that really where it goes? Or maybe it's closer, move the rug to the correct corner or the side of the room. And that same group of students went back and they would push the rug over to the side there. Now, why didn't they do that the first time? This is where I put in a couple geek notes. Human brains process geographic information through multiple parallel pathways. And the network in your brain that processes the idea of enclosure, something's inside something else, like a room, that network seems to finish about a half a second sooner than the network that processes proximity. And those students, when that first network had finished its job, thought they had answered the question. We put the room in, putting the rug in the middle of the room and being proud of it, and then moving it later to a corner when they were prompted to do so, is a great illustration of what we call a mental path shift. And it happens very often with young children. To quote from a very general study of model use by young children, to put a symbolic object, such as a model or a map or a picture, you have to achieve what is called dual representation. You have to mentally represent the symbol and its relation to the object that it represents. That's complicated because human brains use a lot of different networks to process spatial relations. That brings me to observation number 3. How do we know that people use multiple brain networks to remember the location of something? What we did was we hid a treasure. We gave the teachers in a room a simple map. We've got 9 identical books, and they're on 9 identical tables, but the tables are different colors. And this is you. You're standing right here. And I'm going to hide a treasure under this book. In a teacher workshop, I'd had a $50 bill. I don't know why I do this in kids. How are you going to remember where that treasure is? Because we're going to lead you into another room. And it also has 9 identical tables with 9 identical books on it. And we're going to walk you over to stand in front of it right there. And you're going to, is that treasure under table number 1, 2, 3, 4, 5, 6? Those are the 6 tables that different teachers remember that treasure being hidden under. The question is extremely simple. What table has the treasure? And the answer is not simple. It depends on what brain network you are using to do spatial thinking at this moment. If you're using the brain network called proximity, that's on the table near my right hand, you're going to put it on table number 1. If you're going to use an association network, which is in a completely different part of your brain, you're going to put it on table number 2. It's on the orange table. If you're going to use the sequence network, that's in the front of your head, again, a different place. You'll pick table number 3. if you're going to think it's the book that's in the same position on the table, you'll pick table number 4. A little bit more complicated sequence, the middle row or the front door side of the room. That's table number 5. And then a complicated analogy, the book in the same position on its table as the table is in the room. And what's important to note is that I've done this thing in about 15 different teacher workshops. And in practically every single one of them, at least one teacher picked 4 different ones of these places to remember where this was. In room number 1, the treasure was in the bottom middle of the table, in the bottom middle of the room. In this room, it's in the top right corner, the table in the top right corner of the room. And that is a perfectly logical place to put it. Relatively few teachers will pick that because the other networks tend to happen earlier. It also helps explain why standardized testing sometimes doesn't work, because sometimes people can think of a right answer that even the test designer didn't think of. Like I say, I've played this game in elementary schools, college classrooms, and PD workshops for teachers, and people vote for different options. There's a good reason for this. Human brains process spatial information through multiple networks. They work in parallel. They work at roughly the same time, and you're not always conscious of them all. People may access different networks at different times. There's a quote about the visual brain consists of several parallel, functionally specialized processing systems. They terminate their tasks at different times, and they act fairly autonomously. There's a key article from 2004 when we first started hooking brain scanners up to people. Talks about different brain areas, and it was followed by hundreds of articles that talk about individual differences, multiple systems, parallel processing, separate channels, 2 different forms. This joke I would use is, if human brains were simple enough for us to understand them, we might be so simple we wouldn't. The big point for educators is, better or worse, this is the visual system and the brain networks that children use to read maps and graphs and numbers and text. What do you mean by text? Here's a quotation from the director of the largest reading and math neuroscience lab in the world. And he says, visual spatial attention is of paramount importance in normal development of reading. Associations between shapes, orientation, spatial location, left-right order, every one of those things that I've circled in orange is processed by a different brain network. 2 of them in the back of your head, 1 on the right side, 1 above your left eyebrow. Different part of your brain. This principle is also important in learning how to do math. The next quote says, prior research has revealed a robust and consistent relation between spatial and mathematical skills. Spatial training is an effective means for enhancing mathematical understanding. Now, that article was written in 2022. That's fairly recent because we haven't been looking at brains with brain scanners for more than a couple decades now. The bottom line is that the Giants' activities have got a solid foundation in a lot of very recent research about the visual spatial skills that students need to read a map and to learn how to read and to do math. But yes, this research also explains multiple kinds of dyslexia, but that research is still going on right now. So what can we do in K-3 to help students develop these brain networks and to convince a school principal that this is important to do? The Giants website, if you go out onto that website, click on K2 Giants, the first unit has the background presentation that you just saw, plus a couple more presentations. It's got a handful of supporting handouts and other planning resources for teachers. And then there is a suggested fall, winter, and spring unit that can be adapted for your particular community. And it comes complete with explanatory presentations and all the PowerPoints and handouts and things like that that you need. The key message is children use different brain networks to encode visual information in different ways. And that means that they're going to see different things when they look at a map, graph, or photo. And doing a map lesson in first grade can help you understand better what they're seeing when they're looking at mathematics and at reading. Because every child can learn how to do all these different kinds of spatial thinking better. You just have to know how to ask the questions. Because these are the brain networks that are also used to read and to do math. And the websites that we showed you have got a couple posters that you can use. Reading depends on special thinking in a number of different ways. Letters are spatial shapes. They face particular directions. Letters occur in a spatial sequence. They occur with spatial associations. Proximity matters. The White House lawn, it's the house that's white, not the lawn. Text is a spatial hierarchy. And all of those words that I put in bold there are processed through a different brain network. And we now know that because we've been hooking up brain scanners to kids. And I've got another poster for the same thing about mathematics. Numbers are spatial shapes. The number line goes in a specific direction. So if you've got a lesson about direction in the classroom, it's going to help them remember what the number line is about. Numbers occur in a particular spatial sequence. Subtraction is a size comparison. Division is a size hierarchy. And geometry is all about shape and about connections. And again, what I put in bold are processed through separate brain networks in parallel. So if you look at these three projects, classroom maps, read-alongs, field trips, they're actually quite common in early grades. The difference is the specific questions the teachers ask. And the Giants website gives you some planning forms that you can use to guide a discussion about the supporting scaffold questions and the reading and math spin-off questions for each project. So we've got a starter page to get going, and we've got a sample of what the teachers in one school decided. Now, I know you can't read that on the screen right now, which is the whole point of putting it on a PowerPoint later on and on the website. It's not a prescription, it's an example. Teachers have to decide what big projects they want to do, when and how to do the scaffold and spin-off activities. And if you need to defend this to your school administrators, we give you a 2-page handout with 80 key research studies that were taken from a bibliography that now has 4,600 research studies around the world. And what's interesting is the article that my wife and I wrote about this is widely being cited in Korea, Indonesia, Turkey, Greece, Mongolia, Brazil, but very rarely in the United States yet. And if you want to know why some other countries are doing better teaching reading and math, you might take a look at whether we are actually using recent research in how kids process spatial information. Spatial training improves mathematics ability. Spatial coding is needed for visual word identification. Multiple factors in early symbol use. Our final witness is a high poverty public school in Harlem, New York, where a bunch of first grade kids had 40 to 80 minutes of geography every week, and the reading scores and math scores went up dramatically. You can read more about this experiment in this international journal, or use Google Scholar and just put my name and the word pedagogy down, and you'll get a handful of these research articles. And the curriculum website that's down at the bottom that has those K2 units. So I'll leave that on the screen. And thank you very much.